terminology to make sure we're on the same page regarding what is proprioception, right? So proprioception is the awareness of different parts of your body regarding position, velocity, acceleration, etc. So if you think about how human does proprioception, our brain uses a lot of different multimodal sensor information. It will use the vision information. It will use the sensing, or like the inner ear sensors to jointly identify where is the different parts of your body. But mainly, actually, the main source of information contributes to human proprioception is not vision. So if you think about this, basically, close your eye and try to touch your nose or different parts of your body. You can do it very accurately. If you don't, probably you need to go to a doctor or something. All right. Okay. So with the understanding of what proprioception is, let's talk about why we want to enable proprioception for soft robots. Well, first of all, we all know that soft robots, the reason soft robots are so popular is because it has high flexibility and it's compliant, so we think it's safer to work with. Of course, all those advantages come at a cost or a challenge. The challenge for soft robots, in my perspective, is actually the proprioception. And this proprioception challenge is really led by the infinite DOF, which is the high flexibility and compliance. If you think about the traditional rigid robots, the proprioception is quite simple. You have those rotary encoders or linear encoders that can sense some finite, actually low-dimensional states of the robot, like joint angles. You will be able to reconstruct the 3D pose of the robot without using external sensors like vision. Right? But for the soft robots, the first challenge is actually how to represent it. It's because of the infinite DOF, you cannot use like a finite number of sensors to sense each joint angle. You don't even know where the joint is. It can bend anywhere, right? Like this Baymax is my favorite example of soft robot. We're actually collaborating with the founder of Baymax at CMU about this project. So without knowing how to represent it, we don't even know how to sense it. And if you don't know how to sense, you cannot do closed-loop control, which are important for robots. Okay, and people have realized, I mean, we have a lot of experts that's coming to talk about these things today, and people have investigated into this problem for soft robots for a long time. Some of the previous methods are based on finite element analysis. So you basically build a FEA model of the soft robot and then perform the physics-based simulation or calculation. You can represent the soft robot as a lot of finite elements. But then the challenge of that is it's very hard, arguably very hard to achieve real-time computation that roboticists really love. Now, more recently, people start looking to learning-based method, which I just named a few. There's a lot more. You can check the review paper there. For example, in Cornell, people represent the soft robot by a few angles, like the bending angles or twist angles, and then they embed fiber optic sensors in the soft robot body, and then apply a convolutional neural network to regress from the output signal from the fiber optic sensor to the two angles. Researchers from Georgia Tech was even like simplified this problem to just, we only care about the tip position of the soft robot finger. So they also use the and then they just use a very basic neural network multi-layer perception, MLP, to regress that position. The one that is most closest to the method that I'm going to present today is actually from ETH Zurich in collaboration with NYU Current. So they use MLP to predict, instead of just one position, they predict a few more, like a set of key point of positions, and then you can reconstruct the shape of the surface. If you think about all these learning-based methods, one issue, as pointed out by the survey paper, is that they're really oversimplifying the soft robot. Because previously, as I said, soft robots are really good because they have high flexibility, so they have an infinite DOF, and now we're reducing the benefits into just a few numbers, like the bending angles or the tip position. So that's the issue that we're realizing right now. And it's also actually why it's not like people have not realized this. It's just because it's challenging before to really perform more DLF like sensing of the soft robot body. That is the challenge that I'm trying to address today. So if you take a step back and look sort of the overall picture of this problem, we think a more desirable proprioception method for a soft robot should contain the following features. First, and in my perspective, the most important is we should be able to reconstruct the full body shape. We should be able to estimate the full body shape of soft robots. Because otherwise, we lose the whole point of using soft robots. We should just go back to the rigid robots, maybe. And besides doing that, our method should be able to perform high-speed inference or estimation, and also without compromising the accuracy. So our accuracy should also high. And two additional features that are really good to have is our method should be suitable for many different types of soft robots. Now in the soft robotics community, there are a wide range of soft robots. And I'm a newcomer in this domain. So actually, when I read the literature and see so many different soft robots, the first question to me is, as a computer vision guy, I'm thinking, how can I develop a more general, like a general way, so that I don't need to design a new learning method for a different type of soft robot? And the last feature we should have is the inexpensive and easy to set up feature. And then if you think about this problem, it's really we're looking at this three piece of things. The first is, in order to do proprioception, we should have some self-observing signal of the soft robot. And the second piece of the thing is we want to be able to get a 3D shape of the soft robot. And in order to find such kind of a conversion from the self-observing signal to the 3D shape, we need some kind of representation space so that we have a first function h of phi that maps the self-observing signal to a state in this representation space, and then we have another function f of theta that maps from this representation space to the 3D shape of the robot. And this is actually nothing new. If you think about the rigid robot, we actually already have this. The self-observing signal actually comes from the rotary encoder or linear encoder of the joints. And the representation space is actually the well-known DH convention for the rigid robots, which basically records those low-dimensional angles and lengths. But the question is, for soft robots, how can we find a proper type of self-observing signal, and how do we model this representation space? So in our method, we adopt the cameras or images as the self-observing signal, and we propose to use neural networks, a new type of deep neural network based on the Feng net that I just mentioned, to learn the two functions especially the F function that go from the representation to the full body 3D shape. And here we represent the shape of the soft robot as a point cloud, which is basically a bunch of 3D points. So it's an n by 3 matrix. Each row represents a 3D location. Now the question is really, how can we model and how can we learn this representation or latent space? So here are some of the data that we are looking at. In our lab, we built several different soft robots. We start with the most simple one. I always explain to my civil engineering friends that what is a soft robot? You can think of it as a balloon. So we actually use a balloon to do our first initial experiments. But of course, we try different other things like fiber reinforced soft robot and UNet soft robot. And in each of those robots, we put a camera inside, either inside or besides this soft robot. And the second row, you see there's the example self-observing images. And we obtain ground truth 3D shape using low-cost device like Kinect. So you can buy it within a few $100. And this is our data collection system. We have a soft robot with the self-observing camera connected to the computer, and we have such depth cameras observing from the two sides of the soft robot, so we have a complete view of the robot. With this setup, we want to achieve our objective, as I promised at the beginning, is to achieve full body shape estimation. We need to do it really fast to achieve 400 hertz, and we need to do really good accuracy. So we have relative error is less than 5%. It's a millimeter level accuracy, and it's really inexpensive. The whole experiment setup is less than 500 if you exclude the laptop. And it's really easy to set up. And the detail of the setup I will not discuss today. You can read the paper. And we argue this is suitable for many types of soft robots. It's really agnostic to the robot itself. And here what you are looking at, this video, is our end result. I'll explain in a few more slides how we achieve this. But what you are seeing here at the top left corner is the self-observing real-time self-observing images. You see the balloon. Here we're using the balloon, and the inside of the balloon is painted with textures. The gray and dark area are the ground truth 3D observation from the Kinect provided from a third-person view. And the color points are the network's estimation using our method. Blue points means we have small error. Red points have slightly larger error. And all this is run in real time. So how do we do it? Oh, by the way, this moving shadow, it's just my students. It's changing the shape, bending, and inflating and deflating the robot. The balloon, sorry. So how do we do it? I put this small picture there just to remind the whole setup. We have self-observing signal. We want to model the H function and the F function. So basically, the H function here is really easy. We use a ResNet, or a convolutional neural network, to regress from the input image to a latent feature, the latent code C. The real meat is how we model this function F. And that's actually how we used my previous paper, FoldingNet, to model this. FoldingNet basically, I will not talk about the details, we can discuss later in the poster session, but FoldingNet basically is trying to teach neural network to do paper folding. I gave this talk before at CUNY, if some of you attended that session. You all know, basically we're trying to teach a neural network to fold a piece of paper or any 3D surface into other surfaces defined or captured by the latent code. Okay? So a little detail here, what we're doing is we have a bunch of points here, sampled from the prototype shape. Here it's just a half of a cylinder. And then we append the latent code that's supposed to capture the detailed shape of the current state of the soft robot to the end of each location. And then we model the function f as a point-wise multi-layer perception. So it's independently deforming or transforming the points sampled from the prototype shape to the final shape. And eventually, we train the whole network by minimizing the dissimilarity between the predicted 3D shape and the ground truth 3D shape. Okay? So that's the detail of this algorithm. And next, I want to show what is the learned latent space. So here we're basically taking that latent code C, which is a high dimension we use of 128-dimensional code to represent the state of the soft robot. And then we use a dimension reduction technique called TSNE to reduce the dimension to 2D so we can see it. So here what you're seeing, each individual image, the position represents the state in that latent space. And we're showing the 3D shape accompanying that. So you can see that at some region of this latent space, it corresponds to expanding some deflating the shape, and some bending and that. And here are some quantitative results. Due to the interest of time, I think you can check our poster and paper, but basically it's just these figures you show were really good. We get really good accurate estimation, and we're really fast. This is to show the speed. And the good thing of our method is we can decode any resolution of the point cloud. It can be really, really dense point cloud or very sparse, depends on the application. And we also do some hyperparameter analysis that we can discuss more in the poster session. That's the end of my talk. I guess, I don't know whether we have time to take questions. Okay. Yep.
We have time for one question.
How much time do you spend on the training of the design?
Training, well, first of all, the training time we usually don't care, but because you can spend, it literally can spend a week to train the whole thing, and then the time we're reporting here is the inference time. But having said that, our training is really fast. It's a few hours. It also depends on the training set size. I guess we have another question.
Yeah, so it looked like when you you have a large bend, right, a large curve, because your camera in the middle can't see what's happening at the tip, you lose a lot of area there. Is it possible to stack multiple of these cameras throughout the 3D area and to get the full shape?
That's a good question. Actually, I didn't explain. We can do multi-view decoding. So we can actually decode different views.
And they work together to get one full image?
Yes, that's right. Yeah. Right now we're working on directly decoding the full view, the real full body. Right now it's partial full body.
Let's send our speaker, and we can
discuss more in the poster session.
Yeah, thank you. Yeah.